Sharing my screen. Looks like we are good to go. I posted, I'll switch to a student view because it's cleaner. Posted your first assignment. Now I've been pretty hush-hush about this Excel assignment. So there are kind of assignments, two different types of assignments. And so what I want to, wait, screenshot. Oh, that's loud. Saved photos. And I'll bring it in here. I'll add a page here. And dink. I need some lines. All right, there we go. So here, oh man, where is it? It's forever. So here, these are, here's your first assignment. Assignment 1, Introduction to Data. I had forgotten to post it before class on Tuesday when we covered it, and I didn't want to kind of pounce on you with assignments, and so I held off on posting them until before class today. And so because I do want to explain myself, I guess. No, explain a few things first. So if you click on it, it'll tell you the due date, which is on Thursday next week. So from the time that I post it, I give you at least a week. Sometimes more if it kind of works out that way. But in general, you'll have a week to work on these assignments. I do put them so that they show up, but they kind of redid everything so that they'll show up here in your dashboard, but I'm not sure if yours looks the same as mine. Okay. I've got other courses in here too, but and so it shows up with the due dates there. Now they're not linked to the true due date, so if I do end up giving you more time, it won't show up here because it won't let me change that, but it's a recommended done by date that's showing up here. But if you want the true due date, you click there. And like I mentioned last day, or I guess last week, you have 15 late passes throughout the term. Okay. And what a late pass does, you see the, I don't have a pointer here, but you see the redeem late pass. Okay. And so what that does is it bumps your due date by 24 hours. Okay. The only catch is you have to do it before it closes. Okay, but you can do it anytime. If you already know, hey, I'm gonna need more time than that, right? Throw a late pass on there and it'll adjust the due date for you. And you don't have to involve me at all because it'll just do it. Okay? And you can start it. Uh-oh, now I did something that I shouldn't have done. It messes up the system if I go in and I do assignments like a student, but I guess maybe we'll see. So you can poke around here, you can fill in answers, you can close it down, you can come back to it, right? As long as it's not due, then it'll just be open for you to work on, right? And you can flip around through the questions, and you can try them. You get multiple attempts, tells you how many points are available. 3 points, you get 10 tries before it says, oh no, try again. And then even if you use up those 10 tries, you can still try it again 9 more times with 10 tries each. So it's a lot, right? So there's no reason you shouldn't get 100% on these assignments, right? It's work, yes, but they're kind of set up to make you practice, which is always the goal, right? And the only thing that's kind of disappointing is when you click done. So here, progress is saved. And if the due date comes, then it'll just submit whatever was entered previously, right? So you don't have to click done. Yeah.
I don't know if it's just mine, but I can't open that. It has nothing on.
It might be because I went in as a student and I might have bunged it all up. Takes you to a different one? Yeah. What do these things look like? Let's see.
It shows nothing on like I can click it, but then nothing comes up. And it does it on both.
Might be a pop-up thing. Let's see if there was a stamp too. Okay, I fear it's because I was too gung-ho and went in as a student when I'm not a student. You're able to get it open?
I'm good too.
Oh boy. That's worse.
You just have to clear the cookies.
Clear the cookies. We all know what that means. No, but try clearing your cookies if you can figure out how to do that. But like I said, I'll have to talk to Steve. He knows better. Anyways, let me see if I can undo this mess that I've made. But it should show, when you click on it, it should show the due date at least. No? That's strange to me. As if okay. So you're only seeing that top part.
Yeah.
Mark is done. Not this part. Well, I guess the only advice that I can steal is to clear your cookies. I don't know how to do that though. It's okay. We've got some time. The first assignment isn't due until Thursday next week. So we've got time. We can figure it out. Now, what I wanted to highlight in my notes here. So these are assignments. Okay, yeah. Oh, question?
Oh, wait.
Okay.
Just in case.
Just in case I just talked too slow, probably. So there's a difference between assignments and Excel assignments. Okay? And so for statistics, it's really important that we use some sort of software because it's not 100 years ago. And so we have to be kind of comfortable with some sort of software. And for this course, we use Excel just because it's available to you through the school, right? So if you want to download Excel, you get it through the school, and you probably have Word and things like that already. And so you have Excel available to you. And so that's the difference. These Excel assignments are meant to teach you just a little bit of Excel. Okay? Now, we're not covering Excel in the class. Okay? The class is purely theory, okay? Or not purely, but mostly theory, okay? And the tests, so the tests and the final exam will only be on the theory. So there's no Excel on your tests or final exam or anything like that. Okay. And so here, this is not tested. Okay. But these assignments is testable material. Right, so this is theory. Once you get used to using Excel and some of those Excel functions, right, it might be useful for answering that theory testable material, right? Just know that you won't have Excel in the test, obviously, okay, because it's just on paper. Okay? And so the Excel assignments are set up in a way where you read the instructions and you do some stuff and you poke around in Excel. And I tend to give you a little bit longer deadlines on those ones because you are learning something on your own, right? You're learning some parts of Excel. Now, if you've used Excel before, cool, that's awesome, right? Maybe you'll learn something, maybe you won't. It's okay. But probably something new. Okay? Who feels super comfortable in Excel? Couple of hands. Nice. Then you're breezy, but just know most of you kind of feeling like Excel? What? Why? Why? You'll see. It's way faster once you get the hang of it. And like I said, it's important that we use some sort of software, and Excel is probably the easiest one. So these, it's not tested, oh, I should say, and not covered in class. So they're kind of a on your own type of thing. So learn on your own, sort of. You can come see me. I just won't talk about them in class. Okay. And I think I made assignment 1. Assignment 1 is due on September 18th. All my due dates, or all my due times, I guess, are 11:59. So basically midnight. Okay. Midnight gets weird. And Excel assignment 1 is due, okay, I gave you a little bit more time on a weekend, 22nd at 11:59. Nice. Your first assignments. Wow. It's big. There's a lot more. A lot more where that came from. But today we're doing section 2.1. And then notice that on Tuesday, I can never get through 2.1 in one day. And so then we do 2.1 continued and 2.2. So we spend a lot of time in section 2.1. Also, did I answer your question?
No.
No.
It's the first, not the Excel assignment, just the regular one, just answering questions and stuff on there.
Yeah.
It's not a thing that we have to pull up paper and.
No, eventually you'll probably need to do some work on the side in order to answer the question. But for chapter 1, it was a lot of terminology and kind of, yeah, get to know variables, things like that. So, but you don't have to submit any written work until the test. So do a smidge of review, even though it was just on Tuesday. Kind of like a previously on stat 121. Just pull in what we need. So a variable, right, for us can just be split 2 ways. We saw last day that of course we can go a little bit deeper, but for us in this course, right, it's either numerical or categorical. Last day we talked about data collection. So collecting data, what are some things to keep an eye out for? Random sampling is the only way to ensure that we have a sample that's representative of the population. All right. Let me add that here. So random sampling is I shouldn't say only, but let's say the best. Is the best way to ensure the sample is representative of the population. That's an important tidbit. Yeah. Today, we'll introduce summarizing data. So now in our journey, we've collected data. Now what do? We look at it, right? And ideally, we're able to summarize this data, right? And so for summarizing data, we're gonna do numerical data in section 2.1, and then we move on to categorical data in section 2.2. Now, as I probably mentioned on Tuesday, there's a lot more to do with numerical data, right? That we can do with numerical data as opposed to categorical data, which is relatively simple, right? We've got counts. We can go crazy and make them percentages, but besides that, there's not a ton to do there. Okay? So we'll be summarizing visually, okay? Summarizing data. And we'll be summarizing numerically. Okay, so with numbers, we can also summarize things. So that's what's coming down the pipeline. But before we end this review, we also had, so a variable can be numerical or it can be categorical. And then it can also be a response variable or an explanatory variable. Right? And so a response variable is the variable of interest. Now, a response variable can be either numerical or categorical. I used to have a little rubber band that I would put under here so it didn't shake so much. I don't have one anymore. I'll have to wait till later in the term when stuff gets left behind. Oh, you know what? Good idea. I'll just make a little. It's just like the tiniest little wiggle. Okay, this was probably too small. Nice. I think we did it. So the response variable is the variable of interest. In a research study, it's the main one that I'm interested in, right? GPA, for example, tends to be the one that I'm most interested in. What things explain changes in GPA, for example, which leads us to our explanatory variable. You can have you usually have more than one explanatory variable. So any variable that you've collected in your spreadsheet, so any column that's not your response variable is considered an explanatory variable. Right? Some do explain changes in the response and some don't. Right? We collect them either way. So variables, usually more than one. That may explain changes in the response variable. We'll call that the end of our review. Otherwise, we're just doing Tuesday's class again. But that's all we need mostly for today. Okay. Any questions before we start summarizing numerical data? So here, this is section 2.1. So chapter 2 is on summarizing data. And we start with numerical data. It's a good place to start. So we can summarize data. One, visually, or two, numerically. Ugh. So we'll start talking about, okay, what are some of the visualization techniques that we can use? We've seen one already. All right. The scatter plot, giving it away on the next slide. All right, so we've seen some visualizations already. But we can summarize data visually and then I should say, and numerically, right? So with numbers, I can summarize data if I have numerical data. So one way to visualize data, especially if you have two numerical variables, you use a scatter plot like we saw last day. Here's a scatter plot. We can't do this part because the link is broken. But it used to be one of those cool things where you can change the year and see how it changes year by year. And if you have ever seen a talk by Hans Rosling, who's a Swedish statistician who has passed away kind of recently, but he did these incredible talks on visualizing data and just kind of data like this one here. So here, the year is 2011, and we're looking at the life expectancy in years. And the explanatory variable that we're looking at is children per woman, which they're counting as total fertility. Okay? And so what do we see? Well, if you kind of squint, you see this downward trend. Okay? So from last day, we know that's a negative relationship, okay? But we'll talk more about that as it comes up. But what does that mean? So as the number of children per woman, I know it's so crude sounding, increases, the life expectancy is decreasing, right, in 2011. So then you can flip through the years, and usually it's some sort of animated thing where it changes. But like I said, I'm pretty sure the link is broken because it has been for over a year. But do life expectancy, we still get a scatter plot, so it's still perfect. Do life expectancy and total fertility appear to be associated or independent? We see a pattern, so we feel comfortable saying that they are associated, right? If they were independent, it would just be a cloud, just a cloud with no pattern, okay? So here we see a pattern. Therefore associated. Nice. Which was, I guess, a little bit of review still. Before we talk about dot plots, I want to highlight that for numerical data in the future, the only visualization that I'm going to use is a histogram. Okay? And so I just want to scroll ahead to a histogram, blah, 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 blah. Here. So histogram looks something like this. So that's what we'll be using. But I have to tick all the boxes and say, yeah, we talked about dot plots and stacked dot plots and blah, blah, blah. So that's what we're doing. But as long as you're aware that in the future, we'll just be using histograms. I'll make a note of that. For numerical data, oops. We will use histograms to visualize. You know what? I'm gonna say it properly. Visualize what? The distribution of the data. That term distribution is gonna come back to haunt us quite a bit. So I'm gonna throw it in there gently, and then we'll hopefully get there. So to visualize, so for numerical data, we will use histograms to visualize the distribution of the data. For completeness, and only completeness, we introduce two other graphs first. But don't pay them any mind, is basically what I'm trying to say, because none of them are as good as a histogram. Okay. So if we have one numerical variable, such as GPA, right? Got a list of GPAs, then a dot plot looks like this, bunch of dots, surprise, surprise. Okay. And what happens, and you can probably get there just by kind of looking at it and figuring out what's going on here. But as the dots layer on top of each other, the colors get darker and darker. Okay. And so where it's dark, it just means that there are a lot more observations. Now I find that that's really hard to look at, right? Kind of defeating the purpose of visualizing stuff. Right? And so here, if you had to, well, we can say, okay, most of these data points are somewhere between 3.5 and just under 4. Right. And so that's probably as far as I'm comfortable going. All right, here, most points are in this kind of range. It's not very useful, is it? Don't worry about this. She tells you to do stuff, but we're not ready. We'll use a proper graph, histogram perchance. No, we can use the stacked dot plot. This slide, I don't know how it got here. It's out of order. So I made a note that I moved it to later. We will do it, the mean, but not for a little bit. And then we're back to plots, so I don't know what happened there. But the stacked dot plot is a little bit more helpful. Right now, each dot is at least the same color and the dots are stacked on top of each other. It makes it a little bit easier to see what the distribution is, right? The distribution of the GPAs. Okay. So now I can kind of generalize this shape like this. Okay. And I bet you're thinking, wow, I wish I had a name for that shape. Well, you will, but not yet. And so, right, right? We need to talk about distributions and generally, how does the data behave, right? We're not interested in individual points. Notice how lofty I was here, kind of lifting off. Some of that was laziness, but we want to talk about broad strokes, right? So when I see this, even though there's lots of detail here, right? What I'm actually looking for is the general shape of this distribution. If you had to describe this distribution, right, doing your best, you'd probably, again, come up with something like we started with here, right? We see the most points. Okay, that's still true here, right? The largest number of points is kind of, now we have a better scale, maybe between 3.6 and 3.7, right? With the highest GPA being 4, right? So there's kind of a stop there, that's okay. And the lowest being roughly 2.6, right? And so, but a shape would be nice, all right? Just trying to sell you on these shapes before I introduce them, I guess. Well, now we're ready to talk about histograms. So like I said, those other two, they're just a fun ones to introduce. But for us, we'll be working with histograms. But it's good to be aware of the other ones. Extracurricular hours. I'd have a hard time answering this, but the variable, the numerical variable that we're talking about is the hours per week spent on extracurricular activities. I don't know. Does watching a show count? Then it's quite high. Probably not though. Feels like it should be active somehow. Anyways. So this histogram, it's not of the GPA anymore, we're kind of done with that, but behaves the same way as those stacked bar charts, right? And so, or stacked dot plots. So instead of kind of stacking the dots and giving them space to be a little bit off, right? So if I circle, let's say this one here, right? I would consider it in the same stack, but it has a GPA that's a little bit off the rest of the stack. Okay. Now, what we do is in histograms, we just create these bins, right? If you're in this range, right, 0 to 10 hours per week, you go in this bin, right? And we stack everyone, all our observations that are in the 0 to 10 hours per week on top of each other. And then we see that roughly 150 of those surveyed spend between 0 and 10 hours per week on extracurricular activities. So here we see, so the bin width, you can change the bin width and you can change it in Excel. I'll never make you do a histogram by hand. That's crazy, right? I'll give you a histogram to look at, okay? But in Excel, you'll create histograms. And what's crazy about Excel is up until pretty recently, like 3-4 years maybe, you couldn't ask it to make a histogram. You had to kind of jimmy rig it and find workarounds where you did these stacked these bars and then you reduce the space to nothing. It was really hard, but now it's easy. So no excuses. But here, this is our bin width, which in this case is 10. Right? 0 to 10, 10 to 20, 20 to 30. Presumably 10 is only covered in one of these bins, but it'll do that automatically, so it's not something to worry about. And so again, histograms are especially convenient for describing the shape of the data distribution. So back to that shape, and I know it's going to be a major player today. So from this histogram, notice that there's this little tiny stack over here. Someone, it's hard to say if it's one or two people, are able to spend 60 to 70 hours per week on extracurricular activities. Wow, that's crazy. All right, but if I had to generalize this shape, it would look like that. Not being too picky, right? Just kind of looking at the general shape. The thing to remember is that this histogram is based off of a sample, right? A sample of, let's say, 200 students, right? I know it's at least 150, and if I really cared, I could add up the heights of all the other bars. I don't really care. Let's say 200. If I surveyed a random sample of a completely different 200 students, I would get roughly the same shape, but not exactly the same bars, right? And so that's why it's important that you're just kind of lofty with your shape, right? Not too picky with this data in particular. But how samples behave, if they are representative of your population, right, is the shape will generally be the same regardless of your sample, right? So one sample is enough. So the bin width, I always recommend just the default bin width, right? Because usually all our software does a pretty good job of just figuring out what an appropriate bin width is. Okay, but there are times where you have to change it. And when would that be? Well, if you're not getting anything useful out of your histogram, then maybe you need to check your bin width. I'll abbreviate this BW just for simplicity. In this first one, looks like I have a bin width of 0 to 50. So here I have a bin width of 50. This is not very helpful to me, right? Knowing that almost all my data falls in the 0 to 50 category, and very, 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 very few fall in the 50 to 100 category. That doesn't tell me anything, right? And so this, I would say, is not useful to me at all, right? Moving across, I'm happier with this one, right? We've reduced the bin width, looks like it's 10 now. And I'm able to see kind of the general shape, right? And if you're unsure, if you're happy with a bin width of 10, then you can go ahead and you can look at the next bin width of 5. I would say, if I had to talk about the shapes of each of these, this one or this one, I should call them B or C or something, I get roughly the same shape. So for me, I'm happy with either one of these. This one is good, and this one is good. Because notice that we arrive at the same shape. I guess technically you'd arrive at that same shape here, but you'd feel less confident about it, right? And so here, all right, Bing, bing. Get roughly the same shape. So there's no exactly right answer, right? You can play around with it. Okay, but one thing to avoid is something like this. Unless you're really, really good at kind of ignoring noise, which is hard for us to do. What would ignoring noise look like in this case? It would look like this. You'd have to say, yeah, these happened with this sample, but not necessarily with every sample, because there's these spaces here, which indicate to me that, okay, these might be one-offs. That's harder to do here with a bin width of, let's see here, 2, I think. So I don't like this one. If you can believe it, it reveals too much of the data, okay, or about the data. And so here, I'll clarify that it reveals too much. And by that, I mean it's too sample specific, right? Remember, we're keeping it open. If I sampled another sample, I don't expect it to have exactly these peaks. That's crazy, right? Or I guess I'm telling you it's crazy, right? That's not how these things behave. So is too sample specific. Oops. Is what I mean by that. But if you're comfortable kind of really, I don't know, I like to close one eye, kind of just eyeball it. If you're comfortable doing that, that's fine. Then you can use this one. But generally, one of these two is better. So you want to reveal enough, but not too much. The story of stats. I know. So we've already introduced, or I feel like I teased it pretty good, that we need some names for shapes, right? So that if we talk about these shapes, right, then we can have some terminology, right? Not explaining every single little thing. So our first stop there is going to be on modality. Now, a mode is a peak. So the modality would be the number of peaks. Now we're talking prominent peaks. So not like this, and that's where this type of histogram becomes difficult to deal with, right? Because is this a peak? No, but that takes practice, right? Whereas if you have a histogram that looks like this, it's relatively obvious that there's only one peak, right? Kind of at the beginning. So the mode, we can have one mode, unimodal. We can have several prominent peaks. Now notice it has to be prominent, right? So bimodal is 2 modes, right? Or just multimodal would be more than 2 modes. Or no apparent peaks, which would be a uniform distribution. Now, I'm picky. So I wouldn't say that this one is multimodal, but I'll do it for the sake of the example because it's clearly supposed to be unimodal, bimodal, multimodal, uniform. Okay? And so what you want to do, she uses limp spaghetti as her thing that she tosses over. And so imagine that the bars are wooden blocks and you drop a limp spaghetti over them. then the shape that the spaghetti would take could be viewed as a smooth curve, and that's the general shape that we want to talk about. And I tend to talk about, just tossing a blanket over it or just kind of fuzzing it out a little bit, all right? So if we do that, some practice here, I get one mode. Right? Don't get hung up on this little guy here. It's just on the downslope. So this is unimodal. I'm happy with this one. I'm happy calling it bimodal, right? There are two prominent peaks, right? Whether you use your limp spaghetti or a sheet, or you just kind of close one eye. I can't seem to get around it. I get two modes, all right? And so this would be bimodal. And like I said, I could be convinced that this is just, this is just bimodal, but they want it to be multimodal, so I guess I could stretch it there. I'd like to see more of a space here, right? More of a span before the next mode. Otherwise, I would lump those two together. Here, the next one or the last one, you could say, I would be happy with if you said, okay, it looks like there might be one mode, but everything is kind of the same height, right? And so for these modes, they need to drop down. So for that reason, we would call this uniform. Just uniform in distribution. Okay. And maybe I should draw it like this, but not out so far. Ah, you get it. Maybe. So generally a uniform shape. Luckily for us, of course, in the assignment, right, it'll talk about kind of identifying these different shapes, right? But for us, we will be working with unimodal data. Often what's happened, if you have bimodal distributions, is you've combined two groups that you should maybe analyze separately. Okay? So that's usually what's happened. Bringing you back to, right, if this is a group and this is a group, and you split them up, then you have two unimodal distributions. Ah, isn't that so nice? So that's just something to be aware of, but not something that I'll test you on or anything. So for us, we'll be working with unimodal distributions. So for unimodal distributions, I'll write that down. We can discuss skewness. Something is askew, right? Crooked. Okay. So we can talk about the skewness. Now, before we talk about right skewed, left skewed, or symmetric, the only one that we might be familiar with is symmetric, right? And so what we mean by that is symmetric about the mode. Okay? And so around that peak, it looks symmetric. Okay? Whereas a right skew or a left skew tends to throw people off because, or it threw me off when I was first learning it, okay? It's going to be skewed in the direction of the tail. So it's not in the lump where everyone else is, right? Which is usually what we want to talk about, right? It's skewed in the direction of the tail where there's very few observations. Okay? And so here, it's skewed in the direction of the tail. And that's, I find, kind of counterintuitive. Okay? Because as humans, we want to talk about, well, most of them are over here. But in statistics, we want to talk about these guys, these unusual observations, right? That's more interesting. They're the ones that we want to get to the bottom of and see if they're truly unusual, right? And so that's why in statistics, when we talk about the skew, it's skewed in the direction of the tail. And so here, this is the tail. The tail is heading to the right, and so we call it a right skew. Or this is, there's lots of ways you could say it, but skewed right or a right skew. Or if you like to work on a positive negative scale, you can, right? A positive skew or a negative skew. So a positive skew or a right skew. Lots of different ways to say the same thing. Mm. How about the next one? It's unimodal, yes. Looks like, bless you, we've got a little bit of a tail heading to the left. A little bit. We could even throw in modifiers like moderately skewed left, things like that, if you want to get crazy. Slightly left skewed. I'll just say skewed left. Oops. Or if you prefer a negative skew. And then from our list here, this one, say, is symmetric. Doesn't have to be exactly, but if there's no obvious tail, right, then we usually say it's symmetric about the mode. Symmetric about the mode. Right, from the peak, roughly symmetric. Now, we usually only talk about skew if we have a unimodal distribution, right? And so that's why I say we're really only going to work with unimodal distributions anyways. Oh. I'll highlight the note. We already said it, but it's skewed in the direction of the tail, whichever way the tail is going. Most of the time, for us, things will be symmetric about the mode, right? And so we'll give that a special name, which is, so this kind of shape here, we call it a normal distribution. It's confusing because yes, it is one of the more common distributions, but it's actually a name, normal. It used to be called the Gaussian distribution. It still is if you want to be fancy about it. But it's just the name of the shape. Okay? You might have heard of a bell curve before. That's kind of a slangy term for the normal distribution, right? Graded on a bell curve. What does that mean? We will learn, I guess. It means your grades were shifted until it was unimodal and symmetric about the mean, right? Which we haven't got to yet, but it's the average. There, I gave it away. Okay. So as I mentioned, in statistics, we're most interested in these unusual observations, right? So these unusual observations are worth investigating, they're worth analyzing, right? If everything's just as you would expect it to be, then there's nothing worth analyzing, right? But as soon as you have something like this little guy down here, right? Notice that we're not told what the variable is even. That's okay, right? We just see that this is unusual. And so we'll develop techniques to identify whether this is truly unusual or if it was expected from this distribution. Right? Can be a lump of unusual observations. Right? You guys read the book Outliers by Malcolm Gladwell? Anyways, I love Malcolm Gladwell. He writes like stats for fun books. So they're really entertaining to me, I guess, but probably to you as well. And so he has a book called Outliers, and it just examines, successful people and looks at kind of the same upbringing and they weren't successful. So what's the difference? Anyways, kind of a fun book. Malcolm Gladwell, that guy. All right, let's see here. I feel like I was going to say something else about outliers, but how would you describe the shape of the distribution of hours per week students spend on extracurricular activities? We can talk about the mode, right? I feel very comfortable saying it's unimodal, right? And so it's unimodal. And we have this tail because look at these guys down here, right? And so it's skewed right. Or right skewed, you prefer. So for the shape, we can talk about the mode. If there's more than one, then we don't really talk about skew. But if there is just one, then we can talk about symmetry or skewness. Yeah. Just as a summary, we can have unimodal, bimodal, multimodal, uniform, but what's unclear to me at least is that if the distribution is unimodal, then we talk about skewness. Okay. And so if the distribution is unimodal, then we can discuss skewness. Skewness. Should probably all be cleaned up, but that's okay. For practice, which of these variables do you expect to be uniformly distributed? And as an added exercise, let's talk about kind of the shape that I would expect for each of these. So starting with A, the weights of adult females. Now, like I said, the normal distribution, because I've already given it the name informally, I guess, but a unimodal symmetric distribution occurs naturally with many, many, many things, including things like weights and heights, right? Most people hover around the average, which happens to be the mode, right? And then we kind of have some, I think it's cuter to talk about heights, but some people who weigh a lot less and some people who weigh a lot more, but in general, everyone for our adult females are hanging around the center, which is the average. So that's the shape that I would expect for A. The next two requires some inside knowledge potentially, but if you think about salaries of a random sample of people from North Carolina, how do salaries tend to behave? Most people are kind of down here, and then we slope off. And then there's some very rare instances of people making a ton of, hey, why is it making a ton of money, right? But this tends to be, and maybe it's a little bit more extreme than that even. Like that. Same with house prices, right? You might have some that are not very expensive, but then you reach your peak and there are some houses that are very expensive, right? Generally the same shape, right? Unimodal, skewed to the right. So the insider knowledge here is that anything money related tends to be skewed to the right. So any variables related to money tend to be skewed to the right. I say tend because I'm a statistician and I won't commit to anything. But also there are instances where that's not necessarily true, but in general, anything money related is usually skewed to the right. Leaving us with the final option, which is, of course, bless you, the correct option. But why? You've got the birthdays of classmates, the day of the month, and definitely from the 1st to the 30th, let's say, and then maybe 31. But there's fewer options for 31. So we expect it to slope down a little bit, but nothing crazy. And so in general, might have something that looks like this, right? So generally uniform, right? Nice. Good. Any questions so far? Shapes of distributions. I feel like we just did this one, but let's do it again. I crossed out this one because it's too time consuming. But if you have to sketch the expected distributions of the following variables, right? Think about what would you expect to be most common, and then from there, which direction would the data head, right? And so for the number of piercings, you can't have a negative number of piercings. So we'll start at 0. And as I increase, right, a lot of people will have none maybe, right? So we'll make some room for those guys, but a lot of people have their ears pierced, right? Putting you at 2 right away, right? 1 is kind of tricky, I guess, but the general shape that I would expect might be something like this, right? Or this might be at 2 or 3 or something like that. Huh? Scores on an exam tend to be unimodal and symmetric, right? Kind of hanging out, tends to be around the average, right? And so scores on an exam, I'll just do a little one here, something like that. And IQ scores, right? I will say it depends on the course though. A lot of my courses, now you'll know what I mean when I say have a bimodal distribution in the scores, right? Kind of a normal distribution for those who didn't do very well and a normal distribution for those who performed well. And then I've put them together because they're in the same class, right? But they should probably be analyzed separately. So some of my classes, that's just how it is. But in this course, it tends to follow this normal distribution. Same with IQ scores. You can have this kind of average IQ score. And some people have a little bit lower and some people have a little bit higher, and very few people have a lot higher and very few people have a lot lower. Okay. Good. Trying to remember, so if this is moved here. There's something I always talk about, but I guess I'll add a page here. In order to fully describe a distribution, right, we need to talk about 3 things. We need to talk about the shape, we need to talk about the center, and we need to talk about the spread. And I'm just kind of shocked because I feel like I'm maybe missing one somewhere. Nope. I'll snag this one as an example. That might be where I do it actually. Oh yeah, well, isn't this where this is where I paused. I said, oh, there's something I want to say about outliers. Couldn't get there. Well, here I am. Just a couple slides later, I guess. Please stay on the line. In order to fully describe a distribution, distribution, we need to discuss 3 things. One is going to be the shape. So the first thing you'll want to talk about is the shape, right? Is it unimodal and symmetric, which we'll start calling normal, right? Or is it skewed to the left or skewed to the right? Right? And so here it can be either, I like to boil it down to just 2 options, normal versus non-normal. So whether it's unimodal and symmetric, that's normal. Everything else you can just lump into non-normal. And if you feel comfortable, you can specify skewed to the left, skewed to the right, that kind of thing. But the second thing we have to talk about is the center. Hmm. This is just a rough approximation, and you're going to be looking for where the peak is. Roughly, where is the peak? That'll be your center. And we'll have calculations that we can do to find the center, right? And so if we're just describing a distribution just by looking at a graph, then we're just kind of rough approximations. Okay. So if I paste this in here, let's talk about this one here and this one here. I would say both of these are non-normal, right, in terms of their shape. In fact, I would say that they're both skewed to the right. I'll write it down, but just to talk about it, because remember, there's a third one missing. I don't want to write down first. But the center for the first one looks like it's roughly at 2-ish, right? Kind of roughly 2, rough approximations, right? Just eyeball it. Whereas here, right, same shape, but this one is kind of shimmied all the way over and centered around 40. So that's going to make a difference. And we also want to talk about the spread. And again, just roughly minimum to maximum. Just give me an idea of what are some plausible values for this variable. Okay. Roughly minimum to maximum. Okay. So if I have to describe these two distributions, my first distribution I would say is a non-normal, and to show off, I'll say it's skewed to the right. Skewed to the right. Centered around 2. With a spread between 0 and 20. Rough approximations here. With a spread between 0 and 20. Whereas this one next door, good. This one next door, I have the same shape. That's cool. Okay. So we'll start off the same way. If I had to describe it, I would say it's non-normal. And again, it's skewed to the right. But this one's centered around 40. With a spread, whoops. Between I'd be fine if you said 20 to 100, even though it goes a little bit outside that. But it's just to communicate kind of the magnitude that you're talking about. right? Does it go from negative 500 to positive 1,500, right? That's different than 0 to 500. Question.
But like the normal and non-normal, how do you know the difference between them?
So if it's normal, then it has to be unimodal and symmetric. So it has to have that bell shape. And that's the only one that's normal. And then everything else I lump into non-normal. And you'll see why in a second. There. Oh, between, I'll say 0 and 120. So now, imagine you're on the phone, right? And we're on the phone, and I'm describing a distribution to you, right? But in order to describe it, I know this is my phone still, it's crazy. No, it's more of the flip phone. I need to talk about the shape, I need to talk about the center, and I need to talk about the spread. Right? So I'll describe a distribution to you over the phone, and you'll draw it. I'll draw it, but you can pretend to draw it. Or you can try it. Ring, ring. All of a sudden it's a rotary phone. Anyways. Oh, hey. Yeah, no, I'm looking at this data. It's crazy. Yeah, I know. Well, I guess I'm talking to you guys, not this hypothetical person. It's got a normal distribution. Nice. Score. What does that look like? Right away, I know it has this shape, right? Oh, okay. Normal distribution. Hey, that's great. Pretty common, but okay. Where's the center? Oh, it's centered at 30. So roughly 30 here. Okay, pretty close to describing the whole thing. Okay. Now, consider the difference. I'll even copy pasta this here. So if I have a spread, let's say it's between 0 and 50. Okay. Well, 0, 50. I know 30 is not exactly there, but roughly. Okay, roughly in the center, that's okay, right? Just general shapes. What if I said it went from negative 100 to 150, right? That's way more variation, right? And so if I said, oh yeah, but I collected some new data and I had an observation of 100 in this distribution here, that would be really strange, right? Because I'm expecting my data just commonly to be between 0 and 50. Right? So that's one of the ways that we'll be able to identify these unusual observations. Huh? You can see how this was meant to be on the outliers slide. Oh well. I got there eventually. Whereas here, if I had an observation of 100, right, that's right here somewhere. That's totally acceptable and expected even. It's within the range of reasonable values. And so the spread really helps us determine if something is unusual or not. Okay? Part of that. All right. So we've talked about, I'll even add a page here. Talked about summarizing data visually, right? Mostly using histograms, right? And so just talking about the shape and describing these distributions, right? Visual distributions. So now I'm writing it as if I'm going to introduce it all fancy. Now we will discuss how to summarize data, numerical data, numerically. And so we will discuss how to summarize data, I should say summarize numerical data. Numerically. Remember, one of the things that we said to identify a numerical variable is, does it make sense to talk about the average? Okay. And so, of course, the average will be our first stop in numerically summarizing a numerical variable. Did I smudge something too much? Now we will discuss how to summarize numerical data numerically. It looks like numerically, though. Numically, new word. Maybe I'll put this on the new page here. What's interesting though, is the numerical summary that you use depends on the shape. Okay? And so, which numerical summary is appropriate depends on the shape of the data. Which ties back to how we describe a distribution, right? We talk about the shape, and then now not just eyeballing the center and the spread, but now we're going to introduce numerical ways of calculating the center and the spread, right? And so that's why these are just rough approximations to get an idea, right? And then we'll have calculations for the center and the spread, depending on the shape. So I like to do a little table like this. So if I have a normal shape, which is anything that looks like this, whoops. I can never do a beautiful one when it matters. It's because I'm trying too hard. Versus on any non-normal distribution, which could be a skewed distribution, it could be a multimodal distribution, it could be bimodal, unimodal. Unimodal is not really worth analyzing, but can be any non-normal distribution. So here we've got the shape, and that'll determine how we calculate the center and the spread. Now we're going to talk about these one by one, okay? But I just want to introduce them in a table format so that you see them all, and then we'll go back and we'll kind of talk about all of them. If you have a normal distribution, then the best measure of center is going to be the average, which we'll start calling the mean, right? But I use those interchangeably, whatever sounds better usually. It's not, no science behind it, I guess. So the mean or the average, oops, clean that up. So if it makes sense to talk about the mean, then you have numerical data, but the mean is only a good measure of center if you have a normal distribution, because it'll be at the mode. Whereas if you have a non-normal distribution, you can always calculate the mean, but it's not a reasonable measure of center, which we'll talk about later. But a better measure of center is called the median. So if the shape is non-normal, then we use the median as our best measure of center. We can still calculate the average, but I'll show you it's going to be, I'll tell you right now, it'll be pulled in the direction of the tail. And so it's not a good measure of center anymore. For the spread, if you have a normal distribution, then the little buddy with the mean is going to be called the standard deviation, which you may or may not have heard about. So the standard deviation, which we can abbreviate SD if we want. That'll be a better measure or our best measure of spread if we have a normal distribution. If you have a non-normal distribution, we use the interquartile range or the IQR. I never have time to get this far in the first section, so it's okay. But we'll get there. So how we're going to introduce these is we'll talk about the mean. The mean is nice, or the average, because most people, if I give you a set of numbers, you know how to calculate the average, right? And so we'll use that as a foundation for building up the formulas that we have, right? And then we branch out and we calculate the standard deviation. And then we introduce the median, and then we talk about the interquartile range. And so, but here they are kind of summarized. Here it is, the mean or the average. And this is the slide that was, I think, slide number 2 for some reason, or 3. And then I bumped it back down here. So I made a note. I moved it from earlier down to here, if you're following along in those slides. Now, buckle up. The sample mean is denoted as X bar, or it's the name of the variable with a bar over it. In fact, anything with a bar over it, anything with a bar over it is a sample mean or average. So instead of X bar, so we use X bar generically, okay? But if you have GPA as your variable, sometimes we use the variable name. And if I put a bar over it, this is the average GPA. And I like to do this one. Here's your average smiley face. Which I like. Anything with a bar over it is a sample mean or average. In the beginning, I'll say mean as well as average, or I'll try to. until you can link those two and use them interchangeably. Okay? Notice that we've specified the sample. Yeah, because there's also a population mean. And so that's one of the most confusing things about statistics is that, okay, we've got this understanding that I've collected a sample of data, right? Things that I can analyze. But really my goal is to use that sample to learn about the population, right? But that means that my sample is going to have an average. And I use that average, that sample mean, to try to learn about the population mean. But they can't have the same name, right? That would be really difficult, right? So we need different notations for if it's a sample or a population. This is a mu. Yeah, it is a mu. So, why not? So the population mean is denoted by a Greek letter mu. In general, all population information, fun to say, is denoted by Greek letters. And so they're kind of their own thing, and we never calculate them because we never have population information, or we rarely do. Right? And so population information, which is also called a parameter. So any measurement from the population is called a parameter. Notice that population and parameter are both P's. So population information or parameters are denoted by Greek letters. And so mu looks like a fancy M with a little bit more of a slope in the beginning. Like this. MU, if you want to spell it out. And so it's the Greek letter mu. And if you're typing something for some reason, it doesn't really come up in this course, but if it does, you're more than welcome to just type out MU instead of having to go through the symbols and finding the mu, and that's just time waster. Going back to the sample mean, right? Here, your X bar, right? If I gave you a series of numbers, right? 4, 7, 9, 11, and 12, you could find the average of those. What would you do? You would add up 4, 7, 9, 11, and 12. I can't actually remember if that's what I said. And then divide by n, however many numbers you have. Right? And so this is just a way of writing that in math notation, right? Take each of your individual values, add them up, and divide by n. In fact, we tend to take this one step further and say that for x bar is the sum of the x's over n. This is summation notation. Fun to say, fun to do. And it just says add up all the x's, right? Add up all the things after this capital sigma, which says add up all the x's in this case. Well, this is a nice place to start with summation notation. And here I'll just highlight that this is a capital sigma, Greek letter sigma. Oh. The capital version. Yeah.
What's the first word in pink there?
Summation notation.
Okay, thanks.
And it says add up all the x's. Nice. So even if you've never seen summation notation before, you've done it, right? By just adding up all the numbers, right? Then you're summing them, and that's what the notation says. And from last day is your sample size, right? Add up all the things in your list of numbers and divide by the number of things, and then you have the average. And so if we had the population information, we would be able to calculate mu, the population mean, but we never do, okay? And so the practice of statistics is taking X bar, so our sample mean, and trying to learn about mu, right, with some precision. And so the sample mean is what we call a sample statistic. And so notice that the S and the S go together. So if I say a statistic, what I mean is it's a measurement from the sample, right? And if I say parameter, what I mean is it's a measurement from the population, which we rarely know, but we're trying to learn about. Often we'll call these sample statistics point estimates, just to kind of guide us in the right direction of, okay, this is my best guess at what this parameter might be.
Sorry, what is the mu equals M?
Oh, this one?
Yeah.
So here, mu is spelled MU,
Oh,
if you wanted to spell it out. So, and I only point that because sometimes people try to Google MEU, but it's MU and that'll get you there faster. I think MEU would work too, or MEW, I should say. But it's just MU. Okay. We use these point estimates, right? So we've got this relationship of the sample mean, X bar. That's something that we can calculate, right? And we will calculate, right? But really what we're trying to do is use that sample mean to learn about the population mean, right? And then we attach some buffers on there, but that's the goal. And so that's why we tend to call it a point estimate. It's my best guess at what the population mean is. And because we don't have time, and I don't give you a break, I know. I just would never be able to time it properly. So we'll start here on Tuesday. Can read ahead though if you want on the variance, standard deviation. If you have any questions, let me know. Otherwise, enjoy your weekend. See you on Tuesday.
I tried to read about the variant. None of it.
It's okay. That's the goal, remember?